Right. So first of all, great to see you, Yuri, and very sorry I couldn't make it this weekend because I had to do something in Berlin here. But also happy birthday from my side. So very much hope we can soon meet on another occasion. And actually, I did some homework and I saw that we've been collaborating
Sorry,
since.
sorry,
Ca-
Stefan. One second. Okay. So you can continue. You can continue. Sorry, yeah, we had a technical problem here in the.
No worries. Okay, so I was doing my homework and I saw, Yuri, that we have been collaborating since 10 years. So thanks a lot for this. And I also did the homework to find out when we met last time. And I think it was 2022. So actually, this time when you visited, I was in Israel in a sabbatical. But I think you managed to come exactly in the time I had to go to Berlin anyway. So it was very nice to see you there. For everyone else in the audience, so I don't know whether you know, but Yuri has been editor for the bulletin for many, many years, much longer than me. So I joined later. Yuri, do you know how many years you have been in the bulletin editor by chance? It must be like maybe 20 years or so.
More years than your age.
Yes. Thanks. And so this is the latest. Oh, the issue. No, this is the current issue. If someone wants to take a look, that Yuri contributed about interactive classical algorithms, but there are many more. So he had recently something on the measure of intelligence, something on logic and generative AI. So very diverse, and also so his column is about logics in general, and also about cats. So do have a look if you're interested. There are many, most of them are online. And actually, currently, someone in TU Munich contacted me to also make online all the old issues. So probably some more articles of Fury will appear there. So by the way, when I recently looked for something else in the internet, I just discovered that you were also speaking at another person's birthday, Alan Turing's 100th birthday. So that I found this article in NZZ in Switzerland about this. So it was very nice to see. So Yuri asked me to give some overview of our work here that we are currently doing. And the motto here of the work in TU Berlin in our group is we cannot direct the wind typically, right? But often we can adjust the sails. And I want to show you one of these examples in graphs, in dynamic graphs. And actually, oh, there is a question in the chat. Is this for me? Okay. Oh, I think Michael still sees the old slides. Don't know whether I need to do something about it.
You don't. I don't know why. I think that that's on Misha's side.
All right.
Yeah. Yeah. Maybe you have to log out, Misha. Get out of Zoom and enter again. It's probably something. Yeah. Oh. Okay. So Alexander said something. All right. So, but I think that we can continue.
Yeah. So actually, this is a topic where Microsoft and also Microsoft Research in particular contribute quite a lot. So I thought that's also maybe interesting for Yuri from that perspective, I hope. And so yes, this is about communication networks. And just because we mentioned the algebra of Dexter-Cosen, so actually, this is recently also applied a lot in communication networks. So I guess you're all familiar with Netcat. When I was in Aalborg, we worked on some weighted version or quantitative version of Netcat with Kim Larsen and his postdoc, Bing-Tian Pue. But then also we work, for example, on automata theory to verify correctness of communication networks or policy compliance. Because most outages in the internet today, they are based on human errors. So there is a lot of efforts to make automated approaches to make like reliable networks using automation and formal methods. So this is something we are very much working on using like binary decision diagrams, automata theory. Some of the important networks, for example, of Deutsche Telekom, they are based on something like called MPLS. And that's, you can describe this as a push-down automaton or push-down system, a rewriting system, basically. But what I want to tell you is our project that is currently in the issue of the communications of the ACM. And it actually also comes with interviews with some of the leaders in this area, like at Google, at MIT, and at UCST. And this is also our ERC project. So, and actually, this is together with Chenavin. So when you visit us in Berlin, I was actually doing a sabbatical in Israel, and I also was working a lot with Chen, who is in Beersheba, in Ben Gurion University. So a little bit of context. So we are mainly working here on the data center network, and this is particularly critical these days because of machine learning workloads. And traffic is growing a lot there. It's growing explosively because, yes, mainly AI workloads these days, but of course we have many applications running there, and they're all running distributed. And the issue is there is also Moore's law in networking, which means that network equipment is reaching capacity limits. So over time, we get less and less increase of the gigabit per second per euro or per US dollar. So networks need to become larger and larger, have more and more routers and more devices, and that's quite inefficient. And so just to give you an idea how data center networks look like, or data center graphs, there are actually different flavors of it. So this is a set of racks in a data center, and then the question is, how do you build a graph between these racks? And some people, or most data centers today, are based on closed topologies or kind of factories. But there are also hypercubic ones. There are torus-like interconnects. There are expander graphs. So, but all of these topologies, they have in common that they are oblivious to the actual traffic they serve. And this can be quite frustrating. This is like, you can think of it like building a highway that ignores traffic demand. So if you're here on the right in a traffic jam, but there's a lot of capacity on the left, then this can be frustrating, right? And maybe in the evening, it's the other way around. So the idea is to build more dynamic graphs. And one way to imagine it, and actually one technology that was prototyped at MIT, is to have mirrors at the ceiling of the data center. And then you can imagine you have like lasers here on the servers or on the racks. And then if you have a demand like this, where you need to communicate a lot from 1 to 5, and from server 2 to server 6, and from server 3 to server 7, and from server 4 to 8, then you can point with the lasers to the ceiling in a way that you can interconnect the racks exactly, or the servers exactly in the way that there is the demand. So this way you have like a direct connection between each pair of servers. And maybe later the demand changes. It become like this, that 1 communicates to 2, and 3 to 4, and 5 to 6. And then you may reconfigure the network so that it again matches the demand. So that's basically the vision of demand-aware networks or demand-aware graphs, or sometimes also called self-adjusting networks. And the motivation is that traffic demands in data centers, both at Microsoft, but also at Facebook, and most data centers, they are very structured. So the traffic matrices, they are sparse and skewed. And also over time, the traffic is quite bursty. So sometimes you have a lot of communication in that part and then somewhere else. So you can basically have these communication clusters. And if you look at the heat map of the traffic, and then you perform it by clustering, you can even see this structure even more. Basically, we have a lot of small clusters that evolve over time, but not so fast. So that's why it could be very beneficial if you could adapt the network graph based on this demand. And this may sound futuristic, but actually there is technology that allows you to change the graph dynamically. And it's based on photonics, which is like one of the promising technologies of the future prosperity. So there is this both in the Europe and in the US. There's also this saying that photons are the new electrons. So in many areas, there really is a lot of hope into photonic technologies, not just communication, but also storage and others. And there are different prototypes that people have built, and some of them are based on moving antennas, some are based on lasers, and some are based on moving mirrors. And I just want to show you one example a little bit more detail. So the signal is actually not going free space in the data center, but this is like inside a router now, and this is called optical circuit switch. And then you have like light coming in here through the fiber. And if the light is entering the device like this, it will be reflected on the mirror, it will be reflected on the mirror there, and then it will go out on that port. But now what these optical circuit switches can do, you can basically rotate the mirrors. And that's like the technology, for example, that Google is using. And then if the light is coming there, it goes there and it will exit now through the middle port and no longer through the upper port. And that's like one way how you can change the graph. That's another technology. Actually, that's something that Microsoft research has been developing recently, where you have like a laser source, and then the router is, you can just imagine it as a passive prism. And when the laser emits a red wavelength, then it goes like this for the prism and it goes through this port. And if the laser emits a blue prism, then it will go through the prism, blue color, then it will go through the prism and it will go through that port. So that's also a way you can change the interconnect. And this you can actually change the color of the laser within nanoseconds. So this is a very fast technology here. So that's basically the big picture. So we have this new technology and we have this nice structure in the demand. So the idea is like, can we build graphs or interconnects or networks in data centers that can adapt towards these workloads? For example, to provide shorter paths or to improve throughput or improve flow completion times. And I want to show you just some of the combinatorial problems that arise in this context. Yeah, this is how you can imagine it. That's the analog on, probably you know this Golden Gate zipper on the Golden Gate Bridge in San Francisco, that in the morning it will change the lane so that the traffic can go in that direction where there's a lot of demand, and then later in the day it can change the number of lanes again. And of course, there are a lot of self-adjusting systems now in computer science in general, recommender system, algorithmic trading, and so on. But this is like a self-adjusting system that is on the hardware or on the physical layer, which does change some of the assumptions here. Before I tell you, and I think Yuri, you asked me when you were in Berlin back then, before I tell you about the combinatorial problem, I also would like to quickly show you some of the structure and how to measure it. Because when you think about it, how can we even define structure? How can we measure it? It's not completely clear. So this is a 4 GPU to 4 GPU machine learning workload. And each pair of GPUs has a color, and then the height is basically the amount of traffic there. And one question is this traffic matrix more structured? Does it have more structure? Is this traffic matrix more structured? But which one would you say? So most of us would probably say that the left one is more uniform. So it's all the same, right? On the right one, there is more structure. Actually, the first GPU here that communicates more than others, that's like the parameter server. So here we would say this is more structured. And if you look at this traffic matrix and you look at the communication over time, so now this is the communication over time, then on the upper part, I show you one pattern over time, and in the lower part, another one. And if you add up the green, the blue, and the yellow, you will get exactly this amount, okay? So this is the same over time. And this will be exactly the same amount of red like in the upper one. But if you ask which one has more structure, we'd all probably say the upper one has more structure, because here we see some burst of green, here we see some burst of red. And here basically we just sampled this real execution that we saw in a random manner independently from this joint distribution, probability distribution. And so basically here we don't have any structure over time. So one question is like, how can we measure structure in these patterns? And one idea here, or one approach, is to use information theory. So let's say we would take the communication sequence as basically as this sequence here, and put it in a file. And now we could do two steps. One is we put the rows at a random position. So we just shuffle the rows of this sequence. And then as a second step, we also break source destinations. So basically we randomize, or we generate a completely uniform trace where every source and every destination will be chosen uniformly at random independently. And this is a nice way to actually capture the amount of structure we have in the workload, because in the first step, by doing this, we remove all temporal structure. And in the second step, we remove the spatial structure or all other types of structures. We can even do it more dimensional. So these are just 2 dimensions. And now if you compress this trace into a file, you may get a certain size. If you compress this file, it's more randomized, right? So we can compress it less. So the entropy is higher. And then if we compress this file, we even get a bigger file. And then, for example, we can compare, and this is the entropy. If you have a perfect compressor, then this will be the entropy. So if you look at the difference here, this gives us the amount of structure we removed in time. And this is the amount of structure we removed in space. And this way we could, for example, do a 2-dimensional map where we illustrate the amount of traffic structure. So now we get something like this, where we have a temporal complexity or the temporal entropy, and here the non-temporal entropy. And on the upper right, it would be a completely uniform traffic pattern. And now if you can look, for example, at machine learning workloads or at web traffic or other type of workloads, we can basically see where they end up. So this is, for example, from Facebook, different traces from Facebook. This is a machine learning. This is high performance computing. This is a neural network. So they all have different structures, and none of them is really uniform. So today, actually, we build our data centers for this upper right, but none of the traffic is really on the upper right. So if we would be able to build a data center that is optimized to this workload there, we could potentially get a big benefit. Okay, but let's maybe talk about some of the algorithmic problems here. And also here, actually, there's a nice relationship to information theory and entropy. So if you look at binary search trees, let's look at the data structure like binary search trees, then typically we aim to make this binary search tree balanced so that the access cost is logarithmic, right? But that's like oblivious to the demand. So if we would build biased binary search trees or demand-aware binary search trees, we could move frequently accessed keys closer to the root and improve performance. And we could even do this over time. So we could have like self-adjusting binary search trees. If we speak English now, then other letters will be popular than if we change to Hebrew or French or German. So the more we adapt, the better will be the access cost, basically. And the same holds for coding, right? So if you have a worst case coding, then we need log n bits per alphabet entry, per symbol. And if we use Huffman coding, we have the entropy. We are actually the performance will be proportional to the entropy. And there is also something like dynamic Huffman coding that we change the coding dynamically depending on the current demand. And the idea is somehow to do the same for graphs. So now we have, if you have a graph that is constant degree, then the diameter of this graph must be at least logarithmic. So you cannot have like a log diameter in a graph that has a constant degree, right? So, but if you can make the graph demand aware, then what can be the distance of this graph? And if you can make it even dynamic, maybe we can even be better than that. And this is actually more than an analogy. So we have shown that these bounds from data structures and coding, these entropy bounds in particular, they also are transferable to graphs. And basically we can build like demand-aware graphs that have the expected path length or the average path length is based on the entropy of the demand matrix. And I want to just show you one example here to give you an idea. So let's say you are given this demand matrix here, and you see like who communicates to whom how much, and this is a joint probability distribution. So the values add up to 1, and the darker, the more communication. And now we want to kind of minimize the expected path length. So the frequency of communication times the shortest distance between this pair in the network here. So we want to design a network N that for a lot of communication provides short paths, and for infrequent communications, it can have longer paths. So this is basically the objective function. Is that clear? So now, for example, here we communicate a lot between 4 and 5. So it can make sense to have a direct connection between them. Here, server 1 or vertex 1 communicates to all other nodes. So if you have a bounded degree, demand-aware network of degree 3, then we cannot connect 1 to all of them. So for example, 1 is connected indirectly to 7. even though it communicates quite a bit. So we need to make an indirect one. And some of the nodes, they may not communicate at all, but still it makes sense to connect them directly just because it can be a good relay link for other demands to be serviced on. So for example, you could ask like, can you build me a demand-aware network of the degree 3? And then you could, for example, build an optimized binary tree or something like this, because this has degree 3. Or you could ask, what is the demand-aware network or demand-aware graph for degree 2? And if it's degree 2, we can only have like lines and cycles, right? So how can we build a cycle that represents the demand well? So one question is like, how hard is this combinatorial problem? And I think when you visited Berlin, I don't fully remember, but I think we also discussed it very quickly. There is this minimum linear arrangement problem that I guess you're familiar with. And the generalization is called virtual network embedding problem that asks if you are given a demand graph, so this is like a guest graph, how can I arrange these nodes, these n nodes in a line so that the sum of the links are minimized? So what I mean is like, if I would map this node here and if I would map this node there, then I would have to pay 5 hops here of communication. So that will be costly. So it would be better if I map this here and that there. So then that link would cost 1. So if I want to map it in a way that the sum is minimized, then this is like the minimum linear arrangement problem. And this problem is NP hard. And this also means that the demand-aware network design problem is NP hard for degree 2, because more or less degree 2 just give us a line. So you have to, of course, can have rings, but the proof is relatively easy to extend and to see that it also works for rings. So, but then if you can build demand-aware networks of higher degrees, then this become another question. So because maybe this makes the problem even easier. So this is something that is actually quite interesting to explore. What's the complexity of these demand-aware networks? Because embedding a graph on a given graph is often hard, or most of the time hard. But now if you can actually design the graph, this may actually, on the one hand, it seems to make it more complex because you have more degrees of freedom, but it can also potentially make the problem simpler. So just to give you one idea how this problem can be approximated. So if you are given this demand matrix, one natural idea could be that if we just build an optimal graph, demand-aware graph for a single source, like for a single row here, for example, we could build a Huffman tree for this row because this is a probability distribution that is optimized for this source. And this we can compute fast. This we can compute in linear time. And we can do this for every row. So we do this for this row, for this row, for this row, and for all of them, we make an optimal tree that is optimized for this source. Then if we would take the union of these binary trees, then we would have a very nice demand-aware network with very short paths. But the union will also increase the degree. So basically the degree will then be non-constant potentially. So we need to do something extra. So if we take the union and some of the nodes have a high degree, then we need a technique to reduce the degree. And one way to achieve this is basically to take nodes of low degree as helper nodes between nodes of high degree. And this only works if the demand matrix is sparse, which give us a lot of low degree nodes. But, and that's also something that we observe in practice in the data center, that demand matrices are often sparse. But this way now we can use these nodes as helper nodes and basically, excuse me, reduce the degree while still keeping the distance between frequently communicating nodes. And this is nice because if you take these trees optimized for sources, we know that the distance there is always proportional to the entropy. And we can show that for sparse demands, we actually are still proportional. The distances will remain proportional to the entropy. So basically, that's a way to build these demand-aware graphs for sparse matrices. So here is another illustration. So basically, we will have we can also represent the demand matrix as a graph, and then we make an optimal tree, a Huffman tree or a binary search tree for each of these big nodes with a high degree. And then we use some low degree nodes basically to break the degree and reduce basically the degree while not increasing the distances more. And the reason why this is optimal is that you can also define, first of all, you can see that the cost, the routing cost will be proportional to the entropy. And we can also define the entropy on a matrix and not just on a classic distribution. So what we need here is basically the conditional entropy of given the destinations. Let's take the entropy from the sources, and then given the sources, what is the entropy of the destinations? And then we need to take a parameter here, the degree to the entropy. So this is like the conditional entropy. And it follows directly from existing literature in coding and data structures that the conditional entropy is a lower bound for this distance. So that's why this algorithm will be an approximation algorithm, a constant approximation algorithm. And you can even build dynamic graphs, demand-aware graphs this way, because if you take again these trees of all the rows, then you can make each of them dynamic, like self-adjusting trees. And then you can, for example, use classic results from Tarjan and Slater that worked a lot on this demand-aware data structures that basically give you these dynamic graphs. Okay, so this was just a glimpse of this research. So I hope you enjoyed it. This is just the tip of the iceberg. There's really many research questions open here because it's a relatively new field. Like just the question, can we build a demand-aware graph that is a constant approximation if we have dense matrices? So for now, we only know this for sparse. And what about online algorithms? So can we also build like, there is this classic conjecture of splay trees that is open for decades now, whether you can build a dynamically self-adjusting binary search tree that is constant competitive. And especially what is the constant or what's the competitive ratio of splay trees? And similar questions, of course, arise here also. When we talked to Amin Wadat from Google about their recent self-adjusting data center network, which is called Jupyter Evolving, they were mainly concerned about the control of such self-adjusting networks. So how to build like software to really like learn about the demand, adapt it, and control it. Because right now, even though the technology allow you to change the interconnect in nanoseconds, they only change it every couple of hours. So currently, they still try to make it faster, but it's still something that poses challenges here. And of course, if you start to change a graph dynamically and you have something like a routing protocol running on top or a congestion control protocol, you need to think how to adapt those to this setting. And also, how do you make buffer management in a dynamic graph? So if I currently don't have a link, then how long shall I buffer packets there? Because, and this then goes back to other dynamic graphs like they arise in sensor networks or peer-to-peer networks, but slightly from a different perspective here. Okay, so that was all. So thank you very much for your interest.